We're going to solve some more systems of three equations and three unknowns. But this time I'd like to apply kind of similar line of thinking, but I'd like to apply some matrix methods to help us with this. We can solve systems of equations in exactly the same elimination method as we did, but I think using a matrix to represent these systems can be just make your life a little bit more compact and more clean. So what I'm going to do is I'm going to turn this system of equations into what's called an augmented matrix, an augmented coefficient matrix. What that means is I'm going to make a matrix out of all the coefficients that I see in here. So the first row will be the coefficients in this first row. Coefficient of x is 1, coefficient y is -1, z is 1, and then this constant that it's equal to is 3. And often we'll put like a dotted line to represent where the equal signs might have been. The coefficients in the second equation are -1, 3, -4, and -5. And then lastly 2, -4, 5, 7. What's nice about this is that I don't have the x, y's, and z's running around, so I don't have to keep worrying about the kind of the tediousness of writing those out and so on. I know that everything in this first column's an x, a y, a z, and then everything on the right-hand side of this dotted line is what was on the other side of the equal sign. So this just helps me visualize this a little bit more effectively. The same approach applies. I still want to get this in upper triangular, meaning I want zeros in these three spots when I'm done. So maybe just like the first time, I'd like to try to add rows together to try to get zeros here. Unlike the previous example, I already have a 1 here, so I'm not going to bother interchanging rows because I already have a 1 that's easy to multiply with here. I think to get a 0 here, I could take this old row 2 and add one copy of row 1. And I think to turn this 2 into 0, you could do a few things. You could take row 3 and add 2 copies of row 2. Maybe I'm going to take, I like to work from row 1 though every time, that's just the way I've always done things. I'm going to take row 3 and I'm going to subtract 2 copies of row 1 because -2 times 1 is -2. I like to try to work from the same row every time. So what do I get? I did nothing to the top row, so I'm going to just copy those coefficients down. Second row, I just took the middle row and added the top. So -1 plus 1 is 0. 3 plus -1 is 2. -4 plus 1 is -3. -5 plus 3 is -2. I'm going to take row 3 and subtract 2 copies of row 1. So 2 minus 2 times 1 is 0. 4 minus 2 times -1. 4 minus, -4 minus -2. -4 plus 2 is -2. 5 minus 2 is +3, 7 minus 2 times 3, 7 minus 6 is 1. This looks good because I can get a 0 here if I take old row 3 and I add row 2. 0 plus 0 will still be 0. -2 plus 2 will be 0. So that gives me this matrix. 1, -1, 1, 3, 0, 2, -3, -2. 0 plus 0 is 0. -2 plus 2 is 0. 3 plus -3 is also 0. 1 plus -2 is -1. So I'm in upper triangular here. that's good. At this point, I'm going to switch this matrix back to the equations with x, y's, and z's, and then I can use that to solve for to figure out what the solutions to the system are. So if I convert this back to equations, I would get 1x minus 1y plus 1z is equal to 3. 2y's minus 3z's equals negative 2, and 0 equals negative 1. No, this is not possible. Therefore, this is a system of equations that has no solutions. So just like in two-dimensional cases, your system can have no single solution. We'll eventually see when we get to when we talk about we look at vector applications of this that this no solutions might mean that there might mean something something weird, but we'll look to interpret this in other ways as well. But in our case here, this means that the system has no singular point where all three of these equations intersect. Another reason why to use matrices is because you can check your work and actually do this if you have systems where you have all the coefficients defined, then your calculator can row reduce for you very quickly. And I'd like to show you, remind you how to do that. To do that, we need to create our original coefficient matrix on our calculator. On an Inspire, that's in a calculate page, menu, matrix, menu, matrix, create. Matrix. On your 83 or 84, that'll be in the matrix menu, and you want to edit a new matrix. We want this to have 3 rows and 4 columns. And we're going to just enter what all these coefficients were. This was 1, negative 1, 1, 3, negative 1, 3, negative 4, negative 5. This was 2, negative 4, 5, 7. Okay, we'll enter to store it. Your calculator can reduce, get this in reduced row form. So if I go matrix, what's called row echelon form is upper triangular. Reduced row echelon form will be in just triangular form, meaning there'll be ones along the lines. Maybe I'll start with just row echelon form. Then I'm gonna on your 84 you would tell it which matrix you're using, like matrix A, B, or whatever. On your Inspire, I'm gonna do REF. I'm just gonna slide up and highlight the matrix and enter to insert it. And I hit enter, and I end up getting and it automatically puts my matrix in upper triangular. Note that it's divided through by each of the coefficients along the way, so the coefficients up here might not exactly match what we have, but that's fine. But note that the bottom row here is 0, 0, 0 with a 1, just like we had negative 1. But still, all zeros and a coefficient. They divided by negative 1. Again, 0 is not equal to 1. This is not possible. There are no solutions here. So using a matrix to solve a system of equations can be very, very efficient, especially on a calculator portion of an exam. Okay, let's do one more example here by hand. We'll check our work with our calculator, and then we're going to solve a system that you cannot use a calculator for. Again, the reason I'm doing these examples is because you need to be comfortable doing row operations independent of using the RREF button on your calculator, because often you're going to see questions like the final example here where you're going to have a variable as a coefficient, and that's not going to be possible to type in and use your graph calculator to solve the system in the form it's written. So we need to be more comfortable doing the algebra by hand to get through this. I'm going to start by, as I did in the previous example, to maybe go a little bit faster. I'm going to rewrite this as a coefficient matrix. 1, 1, 1, 5, 1, negative 2, 4, negative 1, 0, 3, 4, negative 1. I already have a 0 here. That's good. I'm going to take row 2 and subtract 1 copy of row 1. Did not change 1. 1, 1, 1, 5, 1, minus 2, 4, minus 1. Oh, geez, oh, Pete's. 0, minus 3. I actually need to subtract them. 3 and minus 6. That's a little bit better. 0, 3, 4, minus 1. I got zeros. I need a 0 here. I think I can take this minus 3 and add it with this positive 3 to get 0. So I'm going to take row 3 and add it with row 2. And I get this matrix. 1, 1, 1, 5, because I did nothing in the top row. 0, negative 3, 3, negative 6, because I did nothing to the second row this time. But this time I added 3 and 2. 0 plus 0 is 0. 3 plus minus 3 is 0. 4 plus 3 is 7. Negative 1 plus 6 is negative 7. So we're in upper triangular form. I could just convert here. I do notice, convert back to the equations here. I do know, excuse me, I do know that I look at row 2 and 3 though, and they each have common factors. So maybe I'm going to I'll simplify this a little bit. I'm going to take row 3 and divide it by 7. I'm going to take row 2 and divide it by negative 3 before I'm done with the matrix here. About 1, 1, 1, 5, 0, 1, minus 1, 2, 0, 0, 1, minus 1. So this matrix tells me that this system is equivalent to the following system. 1x plus 1y plus 1z equals 5. 1y minus 1z equals 2. And z equals negative 1. So z equals negative 1. That tells me that y minus 1 times negative 1 is 2, or y equals 1. And that x plus 1 plus negative 1 is 5, or x is 5. So the solution should be x equals 5, y equals 1, z equals negative 1. We can check that quickly in our graphing calculator by using the RREF. I'm going to do menu, matrix, not simultaneous, I don't know why it's doing that. Menu, matrix, create a matrix, 3 rows and 4 columns. And I want the following, I want the original, which is 1, 1, 1, 5, 1, negative 2, 4, negative 1, 0, 3, 4, negative 1. Okay. This time I'm going to just jump right to the RREF. I'm going to use this other reduced row echelon form. This is going to get zeros everywhere other than the major diagonal. So RREF, highlight, pop my matrix in, and I get this matrix. 1x plus 0 equals 5. So x, I can interpret this answer, x equals 5. 0 1y, 0, so y equals 1, and z equals -1, which is exactly what we came up with. So this reduced row echelon form is great if you need to solve a system of equations that you already know all the coefficients for. It's not so great for examples like this final one, where I have a system of equations given here, and note that I know all the coefficients except for this pesky one. There's an a here instead of z, instead of a constant. And the question says find the value of a so that the system does not have a unique solution. And then B, we're going to show that the system has a solution for every value of A. So I think what we need to start with, there's a typo here, that's supposed to be next. Let's start with by finding by trying to solve this as we would, and then we'll try to interpret our answer at the end. So I'm going to start by changing this system into a coefficient matrix. 1, 2, -1, 2, 2, 1, 1, 1, -1, 4, A, and 4. So again, if I want to solve, in an attempt to solve this, I need to get this in upper triangular. I need to get zeros in these 3 spots. So I think I'm going to take row 2 and subtract 2 copies of row 1. I'm going to take row 3 and just add 1 copy of row 1. When I do that, I should get 2 minus 2 times 1 is, I guess copy of the initial row. 2 minus 2 copies of 1 is 0. 1 minus 2 times 2, 1 minus 4 is -3. 1 minus -1 times 2, 1 minus -2 is 3. 1 minus 2 times 2, 1 minus 4 is -3. And then 3 plus 1, -1 plus 1 is 0. 4 plus 2 is 6. A plus -1 is A minus 1. 4 plus 2 is 6. I'm most of the way to upper triangular. I just need a 0 here. So I get a 0 here if I take row 3 and add 2 copies of row 2, because 0 plus 0 is 0. -6 plus 6 plus -6 will be 0. So what do I get? Well, I get the same row 1 because I did nothing to it. I get the same row 2 because I did nothing to it. And I get the following. I get 0 plus 2 times 0 is 0. 6 plus -3 times 2 is 0. A minus 1 plus 2 times 3, A minus 1 plus 6 is A plus 5. 6 plus -3 times 2, 6 plus -6 is 0. So thinking of this as, now can bring this back to equations with x, y's, and z's. This is 1x plus 2y minus 1z is equal to 2. This is minus 3y plus 3z equals -3. And a plus 5 times z equals 0. So the question is, when will this not have a unique solution? Or when will this have infinitely many solutions? I think this problem will have infinitely many solutions if I get a final equation that is all zeros. 0 equals 0 is always true, which means that z could be anything you want, and this bottom equation will always be true, so there'll be infinitely many. So I think there are infinitely many. There are many solutions when you get 0 equals 0 for this last equation. Namely, I'll always get 0 equals 0 when I make the coefficient in front of z equal to 0. So this tells me, so there are infinitely many when a plus 5 equals 0, or when a is equal to negative 5. Part B says, show the system has a solution for any value of a. We've already done most of the work here. Here's the form of our system. When a is negative 5, there's infinitely many, so there's at least one solution. When a is not negative 5, then the system takes the form of x plus 2y minus z equals 2, negative 3y plus 3z equals negative 3, and then something, how about we'll call it kz equals 0, which has a solution. It's just z equals 0, which has a solution, which has a single solution, because z is 0. I plug 0 back in, I plug 0 back in. This has a solution. This has a unique solution. So it either has infinitely many or a unique solution, meaning it never has no solutions. So this always has a solutions, or at least one solution.